Okay, a quick recap of what we discussed last time. We discussed about HMM. So this is the graphical representation of hidden Markov models. We have Z is some latent state, latent random variable, right? And X is our observed random variable. A quick warm up. What are the examples? Examples of X and Z? Huh? Rainfall and season. Rainfall and season. It's a very simple example. It's written here. Temperature and season, or rainfall and season. And X is observed, Z is latent. The condition is that Z should be a discrete random variable. It cannot be continuous random variable for hidden Markov model. That's the condition. And then we saw different components. Basically, we decompose our PDF into these small conditional PDFs. The joint PDF is decomposed. And then we saw individually these quantities, the initial state probability, state transition probability, emission probability, etc. Then we discussed about sampling. Let's say we discussed 3 questions actually. We discussed 2 of them, but one we will discuss today. One question is sampling. If I give you the model, can you generate new data from the model? It's a probabilistic model, right? So which means it's a PDF. So we should be able to sample this PDF to generate more data. That's what we saw in the first part, that the sampling is done in a sequential way. The next we saw inference, which means if I give you some data and I ask you, can you infer the other quantities? Let's say if these are the quantities here. If I tell you what is X4 and what is Z3, can you find the PDF of Z4? Or can you find the estimate of Z4? Right? So we saw 2 kinds of estimates, ML estimate and MAP estimate. So ML estimate is maximum likelihood estimate, which means probability of the observed given the latent. And the other thing is MAP estimate, which means probability of what we want to find given everything else. Right? So probability of Z4 given all the other random variables. Right? So MLE and MAP. And we found that MLE estimate is very easy, but it may not be the best one because it does not take into account the information about Zn minus 1. Right? So therefore we saw MAP estimate, it's able to take into account both the information of Xn and also the information of Zn minus 1. Now let's do it. Let's do the another kind of inference. So generally, what will happen in real life? In real life, you can observe temperature, and you can observe temperature across the entire year, and from there you have to infer what seasons are present. Right? I tell you the temperatures of the entire year, and I ask you what season is on what day. Right? So that is a more general inference problem. Let's work with that. So we are discussing inference. We are discussing inference. And the question, this is the second type of problem we are asking. If I tell you, so basically if we have observed x1, x2, so on up to xn, so you have to infer z1, z2, so on up to zn, right? These are my z's, z1, z2, etc. Zn and these are my x. Right? And if I tell you this, I tell you this, I tell you this, and I ask you what is this, what is this, what is this, right? That's the inference problem, right? So can you write down the ML estimate? Can you write down ML estimate? Write down the ML estimate of z1, z2, z3, zn given x1, x2, xn. Yes? What is that? Teamwork. You can make small groups and you can discuss. Done? Who is done? Raise your hand. Fastest finger. It's so simple question. What is MLE? Oh. Okay, I'll give the answer. MLE is probability of observed data. What is that? Given the latent. And so you will say my z1, z2, so on up to zn star is equal to argmax. This argmax over z1, z2, z basically. That is your ML estimate, right? Right? How many of you were able to get it? Okay. Now simplify it. How will you compute it from your model? How will you compute this from your model? Compute this from your model. How will you compute this from your model? Yeah, good. That's good. So basically you will say, okay, since z1 is given, so x1 is, so first of all you can break this, x1 given everything, x2 given x1 and everything, x3 given x1, x2 and everything. First you do this level of chain rule, and then you will apply the conditional dependence saying that x1, if z1 is given, I don't need anything else, just x1 given z1. And next term is x2 given z2 and everything else. When z2 is given, I don't need anything else. So like that you will, I'm sorry, you should do it in the reverse order, like xn given this, then xn minus, no, I think we did the right way. Yeah, go in this direction. That was correct. Okay, so basically this will become, that direction is important, no? Because otherwise your conditional independence won't hold. You can't say my x1 is independent of x2 given z1. That won't hold. But you can say my x2 is independent of x1 given z2. Okay, so this is argmax over z1 to zn p of xi given zi product I equal to 1 to n, right? And optimizing this is very easy. right? Find out, let's say when we are here, today it's 40 degrees Celsius. What is the season which optimizes this value of temperature, right? And there is no term z1 given z2, which means the temporal evolution has no role to play. That's why ML estimate is not a good estimate. We don't use ML estimate. We rather use MAP estimate, maximum a posteriori estimate. What is that? Yes? What is that? P of?
What we want to find given x.
Yes, very good. So that means P of?
Z1, Z2, Z7 given x1.
Good. Can you simplify this term now? Can you simplify this term in terms of your known quantities? Emission probability, transition probability, initial probability. Done? It's very simple. You've done similar problem before. Done? Anybody? So, do you know SM before? Do you know it? Yes. Well done. Okay, so we don't know PZ given X, but we know PX given Z. So why don't we apply Bayes rule? Right. Let's apply Bayes rule. First convert everything in terms of PX given Z. So this is Px1 to xn given z1 to zn into P of z1 to zn divided by Px1 to xn. That is simply the Bayes rule, right? Now can we simplify? Px1 given z1, sorry, this whole thing, this term we have seen before. Right? Can we write it like that? Product I equal to 1 to n P of xi given zi. So this term is done. What about the second term? P z1 to zn. Huh? The transition probabilities. The transition probabilities, right? Okay. So this is P of z1, the initial probability, into P of zi given zi minus 1. I goes from 2 to n. Divided by P of x1 to xn. How do we write this? How do we write this denominator term? How do we write this? Huh? We know it. Yeah. basically this term is a constant with respect to z, so we don't need to evaluate this term. Means we don't this term does not play any role in optimization, so we can leave it like this. If you want to write it, you can say this is p of x comma z sum over all z, which means the numerator only, but sum over all z. But it does not play any role in the optimization, so we omit this term. So this is right. So that's it. Now this is an optimization problem. How shall we solve it? Let's first try to do some simplification. So this becomes equal to so maximum of a quantity is same as the maximum of log of that quantity, right? We can take log because there are so many multiplications. With log they become additions. Additions are easy to handle computationally. So we say summation of log to the base e probability of xi given zi, probability of zi given zi minus 1, I equal to 1 to capital N, right? And we with the condition that pz1 given z0 is equal to 1 only because no, pz1 given z0 is pz1, sorry, not 1. Right, just a simplification of notation. Right? So basically we have to solve this problem. We have to solve this optimization problem. So if I draw the trellis diagram now, it is like z can take, let's say, 4 values, z1 can take 4 values, z2 can take 4 values, so everything can take 4 values. Summer, winter, spring and rainy season. These are the 4 seasons, and this is n equal to 1, n equal to 2, so on and so forth. Let's say this is one day has one observation. So now you want to find over the year what seasons have happened, right? Let's say you have a long 365 columns. You want to find that from this to this time it was summers, from this to this time it was rainy, from this to this time it was winter, then spring, right? So it's like and what is given to you? You are given this term. This term is a function of what? It's a function of I, like this individual, this term, only this term, inside the summation. This term is a function of I and zi, which means at here, if I am at rainy, then it will have some value. Then I transition from here to here, let's say, from rainy to spring. Then here, this term has some value and this term also has some value. So means every transition plus emission gives me some cost. And I want to maximize the cost. Okay, let's call it as a point, some score. I want to maximize the score. Right? So this is an optimization problem. And how do we solve it? How many possible answers are there? How many possible answers? 365 days are there, 4 seasons. 4 to the power 365 possible solutions. It's exponential growth, right? Can we do something to solve the problem efficiently? So to appreciate this problem, let's draw another problem. So this is an example to inspire you that why we do what we do. This is a field, right? You are starting here from, you can start from this boundary. You have to reach this boundary, and you have to take a path which collects maximum number of points. And the only possibilities are you can either move from left to right, or you can go diagonally upwards or diagonally downwards. Which means if you are at 1, you can either move to 2 or to 13 or to 12. And if there is a boundary, you can't go up. Like from 13, you cannot go up. You can only go to either 20 or to 1. Right? You have to collect points and you have to reach here. And when you reach here, you should have maximum number of points. Right? Basically, you have to select that path or choose that path which will give you maximum number of points. How will you do that? Huh? So there is an algorithm called dynamic programming. How many of you know dynamic programming? All of you know dynamic programming. Okay, good. So dynamic programming. Do you know dynamic programming? No. Do you know it? Dynamic programming, do you know? Oh, behind you, the girls. Do you know? No? Okay. Then this is the time to learn. Learn it now. Dynamic programming. It's a very simple philosophy. Let's say this is a subsection. Let's say I'm sitting here. Okay. The best path to reach this cell, let's call it as the score, some score is there. Let's call it as capital D. Capital D to reach this. Let's say this is I here, or I minus 1 and I. And this is state, what do we call it? Z. Right? So the D means the score at 1, or let's call it the path to reach Zi equal to, which means at the ith instant I am at 2th state. The best path to reach this state will be equal to what? Will be equal to, I have not told you anything else. I just gave you this much information. The best path to reach here will be the best path to reach here plus the score to come from here to here, or the best path to reach here plus the score from here to here, or the best path to reach here plus the score from here to here. Right? Let's say that transition thing is 1 only, because only 3 transitions are possible. Transition has no cost or no score. So only reaching here is the score. So let's call it as this is equal to first this small d means the score here at the zi equal to 2, right, plus the best path to reach zi minus 1 equal to 1 or d zi minus 1 equal to 2 or d zi minus 1 equal to 3. You take the maximum of this, right? You may add here, if there were a cost, you may also add the cost of transition from zi minus 1 equal to, no, not here, but inside. Plus the cost of transition from zi minus 1 equal to 1 to zi equal to 2. Like that, likewise, right? Means appropriately zi minus 1 equal to 2 equal to 3, etc. So comma comma means just ignore transitions for the time being. Just take the this only the cells have emission probability but no transition probability. Okay. So the best path to reach here will be equal to the best path to reach here plus this cost, or the best path to reach here plus this cost, or the best path to reach here plus this cost, right? So this is an inductive, or not inductive, but recursive. This is a recursive formulation of the same problem, right? A recursive way to represent the same problem. All of you agree with that? Do you agree with this? It's a recursive way to represent that same problem. Do you agree at the back, girls? It's a recursive way to solve the same problem. Same problem, but we have written now in a recursive way without loss of any information. Right? Right? And how do you solve a recursive problem? In general. How do you solve a recursive problem? Start from a known condition, like the start from n equal to 0 or n equal to 1, right, which is very trivial case, and from there you start building. Find the solution for n equal to 2, n equal to 3, n equal to 4. In this way you solve the recursive problem. A classic example is Fibonacci numbers, right? Fibonacci numbers are defined as f1 equal to 1, f2 equal to 1, f3 equal to f1 plus f2, f4 equal to f2 plus f3, like fn is equal to fn minus 1 plus fn minus 2, right? So to find any Fibonacci number, you can simply find it in a recursive way, right? So this is how we solve recursive problems, and that same method we can apply here. And this is called as dynamic programming, which means you convert your problem into a recursive problem, and then solving is very easy because you start from z equal to 1 and keep solving it up to z equal to n. It becomes very easy. It is like a linear in time. It's not an exponential problem, but it's a linear space, kind of. Okay, so let's do it that way. Okay, now tell me for this example, what is the solution using this recursive method, dynamic programming? Start from here. What is the best path to reach this cell? The best path to reach this cell from here. This itself, right? This itself is the best path. Starting from here. What is the best path to reach this cell? This itself, right? So we have to maintain two matrices to solve this. Okay. I have to copy it. Let me copy this. How do I copy? Copy. How do I paste? Paste. Okay. Okay. So this is the problem. How do we solve it? We have to maintain two matrices now. One matrix contains the D Zi equal to some number. One matrix contains D Zi equal to K, where K is this. Okay, we have taken it in the upward direction. Okay, and I is this, right? And another matrix which contains the path information. Or I minus 1 to I, sorry. Okay, let's do it. So pay attention now. To reach here, when I reach here, what is the cost? What is the score I have accumulated? 5. Okay, what is the score? 5. And what was the previous link? Nothing means. So this can be empty. Okay. Empty. I'll just copy it here. Okay, now tell me. To reach here, what is the best path? Now you use your recursive formula. Then it's the best path to reach here plus this, or best path to reach here plus this, or best path to reach here plus this. This is not allowed, so let's ignore it. So either this or this. Which one should I take? Whichever has the maximum score. 5 has the maximum score, so take the 5 one. So what is the cumulative score here? Capital D? 18. And what is the link? So to come here, I come from Z equal to K equal to 1. K equal to 1, 2, 3, 4. No, sorry, 1, 2, 3, 4. So previous one is 4. And similarly to come, what is the best path to reach here? 5 plus 2, 7. And what is the link? Yes? Four, no? From 4 we are coming. From 4 we come to 2. So the link to the previous time instant, I have to go to state number 4. Okay, then to 12. To come to 12, what is the best path? To reach here, what is the best path? 9 and 12. So the score will be 21. And what is the previous link? 1. To reach this one, 9 and 1, 19. Score is 19. And the previous link is 1 only. Okay. Now to reach here, 20. So I go from 18 plus 20. So 38 is my cumulative score. 38. And previous link is 4. Okay, to come here, what is the best path? So either 18 or 17. So let's take 18. So it is 19. No, sorry. To reach here, there are 3 possibilities. Either 18 or 7 or 21. So I'll take 21. Okay. So this becomes plus 1 is how much? 22. And the link to the previous path is 2. And then you have to reach here. What is the best path? 21 only, huh? 21 plus 5 is? Can you complete this table fast? Okay, I think I will stop here. Okay, now let's say ignore the last 2 rows. I have to reach here. Let's say my final destination, if it were here. Now, what is the best path? Which one is the best path? Which one is the best path now? Means ignore the, I'm just saving my time. Nothing. Let's say my problem was only 4 dimensional, 4 columns only. So what is the best path? Huh? What is the best path? Huh? Yes, the 59 is the maximum value. So my score, maximum score is 59. And what is the path? Path I denote by pi. That's the notation for path. It's an array of states. What is the best path? So start from the end. At 59, you are at k equal to 3, huh? 3. From 3, I will go back to what? 4, which is here. From 4, I will go back again to 4. And from this 4, I will again go back to 4. This is so 4, 4, 4, 3. Yeah, that's the best path. I got. All right. This is the algorithm of dynamic programming, and in the context of hidden Markov models, it is known as Viterbi algorithm. Viterbi algorithm, right? How many of you have heard of Viterbi school? Okay, so Viterbi school is named after him in USC, right? Many of you apply for MyTex. I think it's MyTex, no? Okay, I don't know. So basically, Viterbi is the inventor of this algorithm, although so for HMMs. So you can solve HMMs using this algorithm. All right. And how do we do it in the case of HMMs? So your D will be equal to, so basically your D to reach some Zi, this is equal to D to reach Zi minus 1 equal to some K dash plus the emission probability and the transition probability of a log here, basically probability zi minus 1, sorry, zi given, sorry, zi equal to k given zi minus 1 equal to k dash plus probability of xi given zi equal to k, and you have to do argmax over k dash. This is a recursive formulation for Viterbi decoding for HMMs. All right. Okay. Clear? Anybody has any doubts or confusions? If you have doubts, just go back and go through it once again. If still it is not clear, then in the next class, please ask. Okay. Now we come to the, what is this? Mm-hmm.
Can you please explain once how to calculate the path?
How to compute the path? Okay, so we know that ideally we should reach here, right?
First one.
This one. So here you will see, if I take some path, if I reach here, if I reach this cell from the optimal path, I will gather 59 points. If I reach here, I will gather only 47 points. Here 28, 29. So let me reach here. Since I am free to reach anywhere on this final thing, so let me reach here only. And the number of points which I accrue is 59. And what is the path which I have taken to reach here? What is the optimal path? That is given by the next matrix. So reaching here means reaching cell number 3 or z equal to 3. So I just note down that z equal to 3 in my array here. Now to reach here, I am coming from cell number 4. My link is to cell number 4. So let me go to cell number 4. I add cell number 4 here. And if I am here, then I come here from cell number 4 of previous I. So 4 is also then added here. Then again go here and then again 4, then again 4. Which means that okay. Sometimes you may constrain that I will start here and I will end here. Right? Sometimes you may say that I only want to start from a particular state and end at a particular state. Or I may start anywhere, but I should end here only. I may fix my end point. Okay, now redo the problem where I have put a constraint that I want to exit from this path. I can enter anywhere, but I want to exit only at this cell. How will your solution change now? How will your solution change now? You have to end only at this state, final of z equal to 1. Yeah, yes. So we start from here. We know my D is 29. My cost or my score is 29. Now let's go from here. Let's go back from here. So to go back, so it will be, my path will be so last entry is 1 that I know. I am sitting here, so I have to go to second state. So this one. So let me add here 2. And if I reach here, again it is 2 and then 1. So 2 and 1. This is my optimal path to reach the last cell. Right? Okay. in practical HMMs, I may say at the end of the year, it is always winters. The 31st of December is always winters. So I want my trellis to end, or this path to end at winters only, right? So we use HMMs for speech recognition. They're very popular for speech recognition, although you can use for so many other tasks also, for any time series kind of tasks, time series classification. So in speech recognition, I consider Z to be, let's say, phonemes, right? So my Z correspond to.
So first you'd have to break it down into different phonemes.
Yes, so any language has a fixed number of phonemes.
So how do you break it down?
How do you?
How do you break the speech, the audio into different?
Okay, I'll come to that. But at least theoretically, you know that, let's say if I'm speaking English, these many phonemes are there. About 50 phonemes are there. Likewise in Hindi also about 50 phonemes are there. They may have sufficient overlap, but still there are many different phonemes also. Like in, can you give an example? Some sound which is, some phoneme which is there in English but not there in Hindi. Okay, think about it. We'll have a class on linguistics very soon. Okay. So Z corresponds to phonemes and X may correspond to some acoustic features. Some acoustic features or parameters, maybe MFCC or log, filter bank energies, or whatever. Right? So X is my observations from the audio waveform, and my Z are the phonemes. They are discrete random variable. Z is a discrete random variable, and there are fixed number of phonemes. So I can use HMMs to decode them. Plus, HMMs give me a flexibility to put a constraint on transitions, right? For example, I can put a constraint that when I'm saying some particular phoneme, after this phoneme, that phoneme cannot come. Just like in seasons we saw, no? After summers, you can't have winters directly. You will have to go through rainy season and then, rainy season and then winters will come. Right? We had put such constraints. So we can put similar constraints on speech also. For example, if I am detecting, if I am only doing number recognition, I can only have 10 numbers. Let's say I'm doing phone number recognition or something, number recognition. I can only have 10 numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. So if you want to say any number, let's say what is the time now? It is 145206. Right? So I can only speak these 10 numbers. So this was the first kind of ASR system which came in market, where it was used in telephones, that people will just say, the questions will be in terms of prompts to answer, that the users can only answer in terms of numbers. Give a rating for our service, they will say 1 or 5, 1, 2, 3, 4, 5. Or tell me the phone number which you want to dial. Then you will say, I want to dial, don't say the whole thing, this the number, 567-231-556, something. And then it will dial it. So only number recognition. Now for number recognition task, you know what are the words. So you know also the phoneme sequences. So you can say in my decoding, in my trellis, only those phoneme sequences are allowed. Other phoneme sequences are not allowed. Right? So in that way, you have cut down your search space. Right? Okay. So that's how. So in
What will be our XI exactly?
our XI will be acoustic features or LFBs or anything which you may choose to make, depending on your computational power.
ZI are phonemes.
Phonemes. Yeah.
That becomes the transcript.
That becomes the transcript. But your transcript will be in the form of phonemes only, not in the terms of words. Right? So to convert them into words, you define that this sequence of phonemes maps to this word. This sequence of phonemes maps to this word. And we generally do it with the help of finite state transducers, FSTs. I will teach FSTs also in one of the classes. It's simply a kind of stringing mechanism where you can string the phonemes into words, string the words into sentences with some probabilistic rules. Just like, okay, anyways. So that helps you to decode more efficiently or find the best path. When I say decode, decoding means finding the best path. Viterbi decoding means using Viterbi algorithm to find the best path. So let me write it down. Decoding equal to finding the best path. Okay. We discussed that we have phoneme sequences, which means every word is made up of phonemes, right? And this is called dictionary. Your dictionary contains every word maps to what phonemes, right? Right? The dictionary tells you what word maps to what phonemes, or the pronunciation dictionary, right? Technically, it is called a lexicon. You can have word sequences that how the words they make up sentences. Okay, or sentences are made up of words. And your grammar will tell you what word sequences are possible. For example, I say I will never say is. I will always say am. I am. I will never say I is Vipul. I will always say I am Vipul. I will never say are. I are going. No, I am going. So many word combinations are kind of not possible at all. So we incorporate that information, and that enhances the efficiency as well as accuracy of HMMs. Let's discuss the final part, training. We started with sampling. If we are given an HMM model, how do we sample new data out of it? We then saw inference. If we are given the HMM model, we are given some observations. How do we infer the hidden states from it? Now let's see, how do we train the model? How do we train the model? This is very interesting. Which means I want to find, training means finding the parameters. What are the parameters in your HMM? Probabilities. So how many parameters? We saw it in the last class. Initial state probability has got k minus 1 parameters. The k is the number of states. State transition probability has how many? K square minus k parameters. And then the emission probability will have whatever model you choose depending on that parameters are there. Okay. So how do we optimize those parameters? That is the meaning of training. So which means you have to find that theta star which maximizes some loss, some objective function, let's say, some score function or objective function. We have not discussed. Okay. What objective function can we choose here now? We are estimating something, no? So we can either use ML estimate or map estimate. Which one should we choose? Map. Okay, let's write down first ML estimate and then map estimate, and then we will decide which one to use. Can you write down ML estimate? So if it were ML estimate, then what will be my L theta? And if map estimate, what is my L theta? Quick. L theta could be anything, just some score. If it is log likelihood, then it is ML estimate, right? If it is a posteriori estimate, then it is map. Yes? Quick. What is my ML estimate? What is my map estimate? Training means you are given the input X and the output sequence. No, you're not. Yeah, you are given the output sequence. Okay. Before I go to training, I want to discuss one more thing, which is related to inference. Many a times, we may be given the phoneme sequence, but we may not be given the alignment of the phoneme sequence with our training or with our input audio. I think that's important before we go to training. So let me discuss that first. It's called alignment. Which means we are given X. And we are given the sequence Z, but there may be repetitions. Like if I say Rajat, right? Then you know I'm saying my phoneme sequence is R, A, J, A, Ta, Rajat, right? But you don't know for how long I said R, for how long I said A. Like A can be over several frames, then J is over several frames, then A is over several frames, Ta is over several frames. You don't know how many frames are there. So you want to find out the exact alignment of your audio with your text or your phoneme sequence or your phoneme basically order given to you, right? So which means if this is x1, x2, x, it may be r, j, Rajat, right? So, but what I am given is only Rajat. I took this example because here it is same phoneme and same characters. So Ra is a phoneme, A is a phoneme, Ja is a phoneme, A is a phoneme, Ta is a phoneme. It may not always be true. Maybe for example I say Sha. Sha is a single phoneme, but in characters it will be SH. So that's why I didn't take that example. Generally phonemes are written like this. Ra, Ra, I don't remember this. I think this is the symbol for Ja. I don't remember. And Ta is, I forgot what is Ta. I don't know. There is some IPA notation for phonemes, phones. Okay, this is the problem, right? How do we solve this problem now? So how we solve it is like this. I build a trellis R. This is n equal to 1, In this way I keep building. Now I put a constraint that if I'm here, I can only make a transition, either stay at R or move to A. But I cannot go back to R after going to A once. From A, I cannot go back to R. I can only stay at A or move to J. Likewise, from J, I can either stay at J or I can go to A. And if I am at A, at this A, the second A, then I can either stay here or I can move to the. I cannot go back. So this is a constraint I put in my transitions and then solve that same decoding problem, Viterbi decoding problem, right? And in this way, I will be able to attain the alignments. This is called forced alignment. Is this clear? Not clear? Okay. So see what was decoding. What is decoding? In decoding, you construct a trellis, this kind of trellis, where you list down all your possible states and all their possible transitions. This makes the trellis. And then you find the best path in that trellis using Viterbi decoding. Right? So this algorithm I know. Now, whatever problem I get, I try to convert it into this algorithm so that I can simply solve it with the same code. So to solve this alignment problem, what I did is, I have my states. Now I modified their transition probabilities.
What is alignment task?
Alignment task is this, that for every frame I want to assign one phoneme. I was given that, okay, input has 10 frames, my output has only 5 phonemes. The sequence is given to me. The ordered sequence is given to me. Alignment means I map every frame to one of those states. So that's how we do it. So it's like finding the best path when the order is given, but not the exact z values for every state, for every time. Double E? Yeah. So actually that double E thing, it's in spellings, but in phonemes, it's an E, it's a single phoneme, E.
So from phoneme to word, will you extract the correct spelling of double E or something?
From phoneme to words. No, from word to phoneme. So actually there is no double E in phonemes. In phoneme, what is there? You have a symbol called E. So let's say if you want to say Sanreeth, then Reeth, it is this symbol. So it will be Sa, A, Na, Ra, then this E, then Ta. There will be some mistakes here because I'm not an expert in IPA. So Sanreeth has only 6 phonemes. But whereas if you write the spellings, you write S-U-N, S-U-N-R-E-E-T. So this is the English spellings, but this is the phoneme sequence. There are 7 characters in the spelling, but actually only 6 phonemes. Yeah, so this problem is not there, but another kind of problem is there. For example, I may say same phoneme twice. Let's say हम आज जाएंगे. हम आज जाएंगे. So j and j, they combine and they make single j. हम आज जाएंगे, right? So that becomes a problem. The sandhi becomes a problem. In Sanskrit, sandhi is very well studied, but in other languages, sandhi is very poorly studied. Even in Hindi, sandhi is very poorly studied. So there is no study actually, maybe. So that becomes a problem. But then there are some methods to deal with it. Okay, training. Let's come to training now. What is training? Yeah, what is the MLE loss, MLE objective function? Quick, have you been able to write it? MLE objective function, and then map objective function. Yes, what is MLE? You become expert in this by now. We have done it so many times. There is no z here, only x and theta. X is observed, and you are given. You are given that. Let us call as y. So this thing, let me call this compressed sequence as y. Y 1 to L. Y1 to L, where L is less than n. L is not same as n. L is less than n. So this YL is given, but Z is not given to me. So for training, x1 to n and y1 to L are given. Z is not given. Yes, so what is MLE? Who has been able to write it? What is MLE? R max P x given theta. Okay. Okay, so for MLE, what is MLE? The observed quantities given the unknowns. So this is probability of x1 so on up to xn given theta. And for map, it is probability of what we want to find given everything else. This is map. We don't know Z, but we will see how we incorporate Z into the equations. So this is what is MLE and map. Simple. Right? Now try simplifying map. If you try simplifying map, it becomes what? Using Bayesian rule, it becomes P x1 to xn given theta into P theta upon P x1 to xn. So basically we are optimizing P x1 to xn into P theta, and here we are just optimizing P x1 to xn given theta, right? So generally P theta may be known or may not be known. Most of the time we may not know what is P theta, right? Which means I may not know what is my parameter probabilities beforehand. So in that case, I may use MLE. But if I know it, then I can use map, which means simply I multiply it with P theta, nothing else.
You mean you don't know the prior distribution?
Yes, prior distribution over theta.
Can't we just assume something like that?
Yeah, we can assume and we can multiply like this, no problem. Okay, but for the, means it doesn't change your solution very much. So we will just solve map in today's class, which is almost over now. Okay, let's.
So what type of problems are we solving? Are we doing a sequence to sequence, sequence to label, or sequence to next element of
We are training our model, no?
So, but for what kind of, I mean, what are the labels?
Labels are YL, like Rajat is given to me. I am just given RAJAT and the audio.
Okay, so we are trying
From
to
audio I can get X1 to Xn. And here I have only a sequence of 5 letters. That's it.
Letters or phonemes?
Yeah, phonemes. Sequence of 5 phonemes. And I don't know exactly which frame maps to which phoneme. But I don't know. So that's what is given to me for training.
Training for alignment.
This is training. Our model also is not trained. Alignment is also not there, model also is not there. Earlier we had at least the model, we could align it. Now we don't have, our model is not trained. Okay. So my L theta is likelihood in this case, probability of. Let's take it as log likelihood. Okay, I'm just doing one simplification. Instead of writing the entire x1 to xn, I'm writing just capital X. Just a short form, nothing new. Now, there is no z here. How do I introduce z somehow? How do I introduce z in my equations? Yeah, take the joint and marginalize, right? That's what we do to introduce new random variables. So this will become log of p of x comma z. Again, this capital Z is a sequence of all z1 to zn given theta and then summation over z. Right? So now what do I do? Huh? EM algorithm, yes. So if my summation sign were not there, if the summation was not there, which means if I knew z exactly, if I had known z exactly, then this was simply a log of px comma z given theta. Right? It was a very simple optimization problem. Why? Because this joint distribution could be factorized and then they're all products, and log of product is sum of logs. Right? Let's do that first because we are running out of time. Assume z is known. How is it known? From force alignment.
So what is our theta here exactly?
Model parameters. All model parameters. Like transition probabilities, initial probabilities, emission probability parameters, everything. So assume that z is known. If z is known, then this becomes simply equal to log of p x comma z given theta. And this becomes equal to so your algorithm will be theta equal to simply argmax theta. Oops. So this is very simple. You want to find all the probabilities, they are available here. Right? So basically this is log of p of xi given zi star right? and optimizing theta, like find the best theta which will give this xi as the output from a given state. It's very easy, simple optimization problem, right? Or in other words, if it is a GMM, I am asking you from this state, you know that this is the state, this is summers, and this is all the data, all the temperatures which you get for summer state, and fitting a GMM to that, is it difficult? Right? So let's say fitting a Gaussian model, let's say. State is given to you, Z is given to you. Just have to find the GMM model for that state. Is it difficult? Or a Gaussian model for that state? Is it difficult? Not at all. Optimizing this, is it difficult at all? You are given all the probabilities. Okay, let me give an example. Let's say I'm giving you a text R A J A T and S A N R E T, then etc. etc. What is the probability of getting an A after a J? So what is the probability that my ith state is A when the I minus 1th state is J? Can you tell from this data? Huh? So there is one occurrence. Please pay attention. It's not very easy. We have one example where A occurs after J. So what is the probability? 1? Are you sure? Okay, let me add some more. This is a very small data set. Let me add some more examples. Just give me a moment. Let's say just some random words. Okay. Tell me what is the probability of A given J? Huh? Quick. 2 by 3? How much? How much? Okay. So what you do is, first of all, count how many times J is appearing. Right? J is appearing here. J is appearing here. J is appearing here. Now you count how many times you get A after J. Here you're getting after J, here you're getting after J, here you're not getting it. So total out of 3 times, only 2 times J is appearing.
So, but probability is a model parameter, right?
This is the problem. Yes, we have how do we call it? We call it as AJK, right?
Right.
AJK. So this is like A from J to A.
So this counting thing would be just one kind of estimator for this parameter.
Yes, this is one estimate. This is a maximum likelihood estimate.
Okay.
Right? This is a maximum likelihood estimate. That's what we are computing. ML estimate. If we choose this estimate, then my likelihood is maximum, which means probability of
like did you prove that this likelihood?
Yes, you can prove it. Yes, you can prove it. You can prove it.
Okay.
That's the homework for you. The next class, we will start from the proving that this is the maximum likelihood estimate of this, right? And this is like a homework. Not, you don't have to submit it, but bring the solution in the class and tell me verbally. Thank you very much. Stop here. Okay. I have some logistic questions before we stop.